it's a number of discoveries, and we will discuss actually 2 of them. The group was led by Burt Richter, and he got a Nobel Prize, and you can see his photo. So, are you checking the photos of the guys who marking somewhere? No, those. So again, in 1974, and what they did is complementary to this experiment. They have measured total cross-section of E plus, E minus annihilation and everything, total cross-section. Remember, slug has storage rings. It's linear accelerator, but it also acts as a collider. Acceleration occurs in the linear parts, but then the electron and positron are injected into storage ring. And here it was a detector, so the beams were intersecting in some place of this beam, of this storage ring. And the detector had the name Mark. Actually, Mark 1. And that made of spark chambers. And shower counters. Remember, spark chambers use this high electric tension, and when ionization occurs, you can visualize the track because avalanches started that you make the photo. And the showers are just scintillator detectors to detect effectively electromagnetic radiation. Now, what is the result? They measured again what I was saying, total cross-section of this annihilation as the function of square root of S. So what happens is that square root of S in this case is just energy of electron plus energy of positron, and this is just 2 energies of the electron in this experiment. This is because centrum of mass system coincides with laboratory frame. They accelerated electrons and positrons up to the same energy. So you collide electron and positron with the same energy, the same momentum, and therefore in lab frame you have total energy in the centrum of mass is just 2 energies of electrons. So you can change regime of acceleration, and therefore you can change the energy up to which you accelerate electrons and positrons, and therefore you can change square root of S. Yeah.
And they really be so sure that they have the same energy, like they're really on the same.
Well, because it's actually in the same cycle, and yes, they have this, yeah. The same cycle, the same kind of configuration, and you have just electron and positron, and they must be accelerate.
Because otherwise we would need to add the extra momentum.
Well, that's actually, yes. I don't know what is the error bar. Probably it's not absolutely perfect, but I think they control, and I think they also have the way to measure it. So what you can do, you can measure the energy of electron and positron. You can use some, this is shower counter, and they are actually, in each event, even they are checking this, because in each event they can put and to see what is the energy release when they have electron or positron hitting the counter. I'm sure that was absolutely under control. So they measured this total energy because they see some events in final state, so they compute, they measure energy and momentum of all the particles in final state, so you can actually also measure in this way. But anyway, so square root of S essentially is given by accelerator itself. And they changed this energy, and therefore they scanned different this square root of S, and what they have found is the following. Again, background related to electromagnetic usual interactions. And then they see not just peak, but they see like a peak with a tail. So it looks like you have peak here and tail. And here is peak. It's kind of complicated peak if you want. So what is interesting that the position of at least this sharp edge of the peak was again at 3.1 GeV. They call this particle psi for the reason is that in some of the events they saw decay of the following type. They saw something like that. That refers to E minus, this is E plus, and this is pi. It's like pi minus, and that will be pi plus. So this is again slightly banded. So that looks like psi. So that's why I call this this particle J psi. So some of the events were of this type in final state. So of course, it was immediate a suspicion that this is the same particle which was also produced at Brookhaven and SLAC, and the name of this particle is J psi, finally. So they didn't agree on something, some unique name of the particle, which is a rare case when a particle has two symbols to denote. So the interpretation of this event is that you have E plus and minus annihilation into single particle. So when you can see such a peak now in the production channel, that testifies for production of single particle, which then decay into some final state. The tail is due to production of additional particles in this annihilation. You have a plus and minus. And then what you may have, again J psi, but also photon can be emitted, gamma. And so you have final state for decay of J psi. Still this effect is enhanced because of presence of this single particle. And you will see the origin of this peak is the resonance, also propagator essentially of this particle. But on the top you have gamma, and that produces some enhancement here above the peak. Okay? So which means that you have enhancement for square root of S, which is bigger than the mass of J psi, right? So to produce photon, we need a little bit more energy, right? And therefore, those events appear when square root of S is bigger than the mass of J psi. But so it was not by far clear what is this J psi. So it required some exploration and detailed studies before it was concluded that this J psi is it is some hadron which consists of charm anti-charm quark. So J psi had the channels of decay into E plus, E minus, but also pure hadron decays. So this is hadron particle. Precise value of the mass is 3096.81. Now I think it's even better now. MeVs. So it's 3.1 GeV, roughly speaking. Gamma decay rate is 0.087 plus 0.0005 MeVs, and gamma over the mass of J psi is 3 × 10⁻⁵. So it's a resonance, but it's quite narrow. And again, what I was telling, they didn't measure really the width of this resonance because energy resolution was not so good, and they just measured the lifetime of this particle. Now the interpretation is that this is composite state of new quarks. Interpretation. So this is new particle which consists of new quark C bar, which annihilate into final state E plus E minus, or it can be produced in this annihilation of E plus E minus. It was measured that the spin of this particle is 1, parity and C parity is minus and minus. Now, that was questioned yesterday. Actually, a number of portion of the channels of this type, when there is an E plus, E minus, is just 6%. So J psi decays into E plus, E minus in 6% of the cases. So they had also mu plus, mu minus decays, and they have also hadronic decays in the final state.
But in the Brookhaven experiment, they only look at the electron channel, so they only see.
But then later they also measured mu plus and mu minus appearance with this. So it's composite state of charm, anti-charm. And then new quantum number has been introduced. Which is also called charm. So that C quark has quantum number 1, anti-quark has -1, and the particles, quarks, which we have discussed before, U, D, strange, they have 0 charm. Okay? So the charm of U, charm of D, charm of S are 0. So it's kind of already extension or analogy. We have observed strange or particles, mesons with strange quark. We introduce quantum number, strangeness. Now we introduce new quantum number, charm. J psi has 0 charm. Charm of J psi is 0. And so this meson is called the meson with hidden charm. Also there are particles with a hidden strangeness, which consist of S bar, and here is a charm bar. Mass of charmed quark is from 1.2 to 1.3 GeVs. Now let me say a few words about the masses of quarks. We haven't discussed masses of U, D, and S quarks. So this is kind of subtle point how we introduce masses of the quarks. Essentially what we are discussing here are masses of just parameters which appear in current algebra. I don't want to kind of elaborate on this more. But the mass of, say, U quark and D quark is not 1/3 of the mass of the proton. It turns out that the mass of the proton, mostly due to interactions. The quarks have very small masses. U quark has maybe the 3, 4 MeVs, d quark 11 MeVs, and most of the energy of proton and neutron is due to interaction. So this is interaction energy, interaction of quarks with gluons. I will mention this a little bit later. So, however, the heavier quarks are, the more they are contributing to the masses of corresponding hadrons. And the point is, and we will discuss this asymptotic freedom, the bigger the energy, the weaker strong interactions become, and therefore at higher masses of hadrons, the contribution of masses of quarks becomes bigger and bigger. So you see this particle has the mass 3.1 GeVs, and each of the quarks has, say, 1.2 to 1.3. So it's bigger already part of the mass of J psi is made of the masses of the quarks, and the rest is interaction, energy due to interactions. So this is an important thing. And first of all, it fits very well the bound which has been obtained from flavor-changing neutral currents. Remember, we discussed this K0 decay into mu plus, mu minus, and then to get strong enough suppression of this decay, we need to have delta m squared. Remember, gene factor, delta m squared even. Not big enough, and it was bound that it should be around 1 GeV, then you can reproduce correctly decay rate of K0 into mu plus, mu minus, and that fits well this estimation. Actually, that was one of the reasons why this identification of J psi with charm, anti-charm, has been made. Interestingly enough, even Miami has written the paper by that time giving different interpretation of J psi. So it was not obvious immediately that this is composite state of charm quark and anti-quark introduced before. So again, it's not straightforward. People tried different possibilities before they were convinced that this is correct interpretation. So you see events, you measure the properties of these events, you measure mass, spin, P, and then decide what is this. So there were several different interpretations, and eventually what was finally established is this charm, anti-charm. Quarks, which appear also in this decay of K0 into mu plus, mu minus. And also quarks, which form doublet with orthogonal combination S theta. Remember, that was introduced on the basis of quark-lepton symmetry. Now let me say a few words about charm spectroscopy. J psi was just the beginning. It is of course not the only particle which has a charm quark. And now you can build by yourself different hadrons which contain charm quarks. So let me take charm, and you can consider composite states of this charm with U, D, and S, right? So that would produce for you mesons. And also you can consider a combination of charm with two other quarks of usual type. Then you will get baryons. But let me focus first on the mesons. So you have also charm, which can be combined with U bar, D bar, and S bar to get particle with baryon number 0, and this is what we call mesons, right? So you see, you may have all these combinations, and you also can have combination of charm and charm bar and charm. So now let us consider the states with spin 0. Remember, J psi has spin 1. But you also can first create the states with spin 0, which you expect are the lowest mass states and the simplest one. That would be analogy with pi and k mesons we discussed before. And so what you will get here, something which is similar to k meson story. You may have particle with charm and anti-d quark, and this is what we call d plus. So we call these mesons which contain charm quark d mesons, mesons with spin 0. Okay? Now we can have the combination charm and u bar, and this is what we call d0. And these two mesons form isospin doublet, because you see this, you have u quark on u bar and d bar, and these are carriers of isospin. And therefore, this quark d plus and d0 will have isospin 1/2, but they also will have charm. Okay? So now we can introduce another combinations, charm u, which is d0 bar, and d minus, charm and d. And again, these two particles form isospin doublet, and they have charm -1. So these two d mesons have charm -1, this +1. Okay? So again, this is similar to the system of k mesons. We also have two doublets. So that here, iso doublets. So on the top of this, we can introduce ds method, which has a composition charm and s bar, and ds bar with composition charm bar and s. So those particles are singlets of isospin, because neither c nor s have isospin, right? They have 0 isospin. But these particles carry charm and strangeness. And finally, we can introduce scalar, which contains c and c bar. So in contrast to J psi, they have the same quark content. However, this is the state with spin 0. Okay. What else? It seems we kind of explored all combinations, right? So here are isosinglets. Those particles, apart from this, have charm. So we call these particles with open charm. Here again, charm is hidden because total charm is 0. Also, the particles contain two even charm quarks, charm and anti-charm. So, and in all, the rest, you have open charm. Now, let me write that those are the lightest particles which contain the charm, and the masses of d mesons are 1.869 MeVs. So that's approximately 1.9 GeVs. It's about 2 times heavier than proton. And they are lighter than J psi. So these are the lightest charm particles.
Does J psi not compose of C and C bar?
Sorry?
What was J psi composed of?
The same C bar, but the spin is 1. So they are in the spin 1 state.
And are you also saying J psi is a meson? Or?
Yeah, J psi is a meson because baryon number is 0. You know, this is definition. Baryon number is 0. It's a quark anti-quark.
But they introduced a new kind of quark, which was not in our picture of SU3 with UDS, and they do not have any place on the
yes. Now I will discuss precisely this what you are telling me. So remember we had before 8. I make notation. It's clear?
Which ones are spin 1 and spin 0?
So in this, everybody has spin 0. So all these particles which I have discussed have spin 0. For spin 1, there are similar notation but with stars. So they put D star, so that to distinguish the spin. So I just focused on the particles on the hadrons with spin 0. They are the lightest actually, and the easy produced particles. Okay, so what is important that we have here 7 new particles, right? So it's 7. Altogether it has 7 new particles. And they have the same properties, essentially, with properties of pi mesons or k mesons. And you can actually add them to the same family. Of course, the difference will be because they have charm. So if we add 7 to 8, we will get multiplied with 15 particles, 15 mesons. So now let me elaborate a little bit on classification. So remember we had SU3 flavor group and fundamental representation and 3 particles, 3 quarks, U, D, and S are transformed under fundamental representation of this SU3 group. Now we introduce 4 quark, and so we can think about extending our multiplet U, D, S, and add charm. And say that probably the flavor group not SU3 but SU4. And those quarks are transformed under fundamental representation of this SU4 group. What does it mean? What is the sense? Again, the same story. So we keep in mind that it should be eventually some Lagrangian of our theory, which should be invariant under this SU4 now transformations. This means that strong interactions of U, D, S, and charm quark are the same. So this is the meaning of this. And this is the meaning that strong interactions of all these new mesons are the same, strong interactions. The difference, by the way, SU4 has a fundamental representation 4 and adjoint. What is dimension of adjoint representation?
The number of generators, which is 4 times 3 over 2.
Well, easy. Make it easier. So, remember, once we have 4 components, then high representation can be constructed as 4 times 4, right? Which is 16, which can be decomposed onto irreducible representations as 15 plus 1. And you see, adding these new mesons, we have precisely 15 components. Now, all these mesons which I have written before, presented before, form, together with discussed before, 15 plet, which is transforming under SU4 symmetry group transformations. Okay? Now, there's one problem. When I'm saying this SU4 flavor symmetry, I'm referring to interactions, but not to mass terms. So remember that Lagrangian has interaction terms and then mass terms. Mass terms break this symmetry, and with this mass, big mass of charm quark, the symmetry is badly broken. So Symmetry refers essentially to the interaction terms, and since the mass of charm quark is bigger, much bigger than the so-called scale of QCD, which is around 0.3 GeVs, that testifies that the symmetry is strongly broken. So one should really take into account the masses of charm quarks, exploring the final consequences, because if the symmetry would be exact, then you would have the same masses of all the quarks, the same masses of all the mesons, which we constructed, and it would be the same cross-section or connected cross-sections, decay rates, etc. So, however, due to this breaking of the SU4 symmetry, you would not have real qualities of cross-sections and decay rates. I will comment on this QCD scale later when we will discuss gluons. Now, apart from these mesons with spin 0, also the vector bosons have been discovered, and this is what I was saying already, that they were denoted D stars, and actually J-psi form also their own multiplet with these particles. Also, charmed baryons have been discovered. In one example I mentioned, no, not mentioned, so this Lambda C, for instance, which is composed of charm, U, and the D quark, for instance. And there's a family actually of these particles. Let me say a few words about decays of D mesons. Which have similar feature with decays of strange mesons. As in the case of strangeness, we find out that charm is conserved in strong interactions and electromagnetic interactions. The same story is with strangeness. But it is broken by weak interactions. So, how do we know that they are broken by weak interactions? Well, the point is that if they would be conserved, then D mesons would be stable. D mesons are the lightest charmed particles, right? And so, since particle can decay only onto something which is lighter, and if there is no lighter charmed particles, and if charm is conserved in all the interactions, then these particles would be stable. However, they decay. And they decay due to weak interactions. So, examples of this decay is D plus can go to K0 bar, L plus, and neutrino. And this is quite similar to what we had for strange quarks when K decayed into pi and then the pair of leptons. Or, for instance, D0 go to K minus L plus and nu. So, also it could be the process when in the final state we have pi, so it can be pi 0, L plus, and neutrino, and here pi minus. So let me put here, no, to avoid the confusion, it can be this also decay to pi minus L plus and nu. It can be electron, it can be also muon pair. The lifetime of this process is around 10 to the minus 12. So the lifetime of d mesons is 10 to the minus 12 seconds, which is typical lifetime for decay of particles due to weak interactions. Of course, it is much faster than decay of K meson. Remember, for K meson we have 10 to the minus 8, and the reason is difference of masses. And remember, this is three-body decay, and therefore decay rate is proportional to the energy released into fifth power. So that explains the difference in lifetime of these particles. So remember, we introduced charm, and this is actually also the way how we convinced ourselves that all these particles are really this charmed particles, and J psi has a correct interpretation. We introduced the doublet with charm and the combination of D and S quarks. So I put for this, and we'll put in further this cosine theta capipa, and this is sine theta capipa, just for brevity. Okay? So when we put this doublet, this means that there are currents formed by this transition, which give this transition and a transition of this type. So transition of charm quark to S quark and charm quark to D quark, and vice versa. In particular, let us try to write what is this D plus decay. So we have D plus, which contains charm and D antiquark. And then this decay can be due to the following transition. So charm go to S quark and emits pair of L plus and neutrino. And D bar is spectator here in this case. So this is K0 bar. So you can construct also the diagram for the second process. So you see here we have these four fermion interactions, which we have discussed at length. So we have this coupling, which should be proportional to the transition of CS here in the doublet, which means that it should be proportional to cosine theta capipa multiplied by G Fermi, because everything is G Fermi and then multiplied by this mixture. So it could be decay when you have non-strange particles in final state, so this charm then transforms into D quark. So it can be this type of the transition. Here we have again D bar, and here is D bar. And this is the component of pi 0. Again, we have here L plus and neutrino. Now, this coupling will be proportional to sine theta capipa. And therefore, the decay rates of this and that ratio of the decays would be proportional to cosine square over sine square. So this type of decays, when charm mesons transformed into usual, are what we call capipa suppressed. So gamma non-strange over gamma strange in final state is proportional to sine square theta capipa over cosine square theta capipa. And this is approximately 0.05. And of course you need to take into account also kinematical factors, because here we have K0 and here is pi 0, but the masses are not very close to the mass of the D meson, and therefore in the first approximation you have the same phase space, and therefore the rates of this decay over these are given by this ratio. So, and again the same story as it was before. Heavier charm particles can decay due to electromagnetic and strong interactions, and they form much faster. So it's D mesons, which are the lightest. They can decay only by violation of charm, and therefore due to weak interactions only. Okay, questions?
How do they produce these particles? Like they are not.
Well, you can produce them in what we call beam dump experiments, if you want. It's just collision of protons with staggered hadron collisions. So you produce them, and if you want to enhance signal from these particles, you have put a big target made of heavy elements, so all long living particles have no time to decay, and you eliminate the signal from the usual pions.
All these charm particles, charm spectroscopy and everything comes from the theoretical prediction of Glashow and the others.
Well, actually, Glashow, what he did is, other people did these detailed studies. Actually, what Glashow did, they used this symmetry quark, weapon symmetry, to introduce charm quark and also explain K0 to mu plus mu minus, introducing this charm. But then that was more or less straightforward. And once you introduce this quark, immediately people start to kind of to build this state. So this is as trivial as we did this on the blackboard, right? So you have other just produce combinations of charm quark with all other quarks. Of course, it took some time to observe this, but they all were observed, and the masses are measured, and so spins are established, and you can find this particle data group where all these mesons are staying, and lifetimes were measured. Actually, these days, a huge number of events of this type have been found. Okay?
At the beginning, the quarks ULD have the same mass, more or less.
No, so I have not discussed this again. For U and D, I mentioned 4 and probably 11 MeVs. For strange quark, the mass is, again, it's not very clear, but maybe something like 120 MeVs. It's heavier. It's still smaller than the scale of QCD. So for these 3 quarks, this SU3 flavor symmetry is a good symmetry, right?
But then we have a quark which is a lot heavier than the other 3.
Then we will discuss also B quark, which is even heavier, yeah.
But then this other.
And so you can do spectroscopy if you want. I can give you homework. So we will then discovery of B quark, and I think for this it will be trivial. In half an hour you can elaborate the spectroscopy in a sense to write up all the states, right? And for multiplets. Yeah, sorry, you wanted to ask something.
That now we have this quark which is a lot heavier than the others, so we broke the symmetry. But then we may think that the other quarks that exist should have this kind of the same symmetry to have this 2SU3 symmetry.
Oh, so no. So
No,
then it will be SU5. So when we add big quark, it will be already SU5 symmetry, which is even broken much stronger, because the mass of big quark is even higher than the mass of charm quark. And top quark. Okay, so.
Should we say then if it's broken there is a symmetry U4, U5? Is it important to talk about the symmetries?
Instead of SU2. Instead of SU, you want to have just unitary, or what is? No, but still you have, or you want to say that what is the sense if it is broken? Even, so we are living with broken symmetries practically everywhere. And still there is some sense to talk about the symmetry, although it is broken. Although it is broken, you still can find some consequences and nothing is wrong. You can take into account that the symmetry is broken. In some respects, you can still have a number of consequences, because charm is heavy, but then it has decays into lighter particles, usual. And their amplitudes of these decays are connected because for light particles this flavor symmetry is good. But you should take into account that the symmetry is broken by mass terms, not by interactions. That's what has been found.
Yeah, part of all of that, there is also the SU3 symmetry associated with the color.
Yes.
Where
Yeah.
that's a total.
And you should not
discussion.
confuse this, yeah. So there's another, but that we will discuss this.
But all quarks that we give names, we think that it's a new kind of flavor. Like UDS, we until now had, and we put some charm, or maybe we will put the other one.
Yeah.
It will be a new kind of flavor.
Yes. Yeah.
Flavor.
Yes. And this the group is SU4 flavor. This is what they are
But
calling.
we do the spectroscopy, but meson and baryon structure is defined in the same way, always, independent of how many flavors.
Well, they defined in the following way. So mesons are quark-antiquark composite states.
Even
That's
though-
how
even though
baryon number is 0. Baryons are made of 3 quarks. But then you can put all these kind of combinations of known quarks, which are now there are 4 quarks.
So it's independent of which SUN we are in. We always have quark and antiquark.
In the meson.
Like for example, in SU4 picture, we have 4 and 4 bar representation,
Yes.
which are the fundamental ones, and we can go like 5 and 5.
Yeah, that will be 5 by 5. Yeah. Then it will be 24 multiplied. 25 minus 1. That will be a join. So then it will extend it in the family. Okay? So now we will go to discovery of tau lepton. Tau lepton has been discovered in 1975 at SLAC with the same machine with Stanford Linear Accelerator. And the group was led by Martin Perel. And for some reason, I'm seeing his photo every day when I'm going down, because it's kind of an invisible place here on this stair you can pass. So he got Nobel Prize for this discovery. So what are events? So they studied the plus and minus collisions and studied what are final states produced in these collisions. And among many different events, what they have observed, E plus and minus, go to mu plus E plus what we are calling nothing. Nothing means not nothing, but it means that there is energy loss and there is momentum loss. So we know what is the energy and momentum in the initial state. So total momentum is 0, energy is known. It's given by the energy of your beams. And then in the final state, you just observe only 2 leptons, muon and electron. Of course, there were events when you have muon, and electron and electron. But this is not very suspicious. That's what you expect, right? There are many ways to generate these events. So electromagnetic interactions. So that's what has been observed. And then they started to study properties of these events. What are the properties? First, is of course violation of lepton number of LE and also L mu, right? At least for visible particles. Second important feature is that this reaction starts from energy which is higher than threshold energy. So it has a threshold energy, square root of S TH, which is given threshold, which is given by just two energies of electron or positron. And this energy, threshold energy, is 3.6 GeVs. So there is no events of such a type when square root of S below 3.6 GeVs, and these events appear when the energy becomes bigger. Okay? So this means that each of these beams has the energy 1.8 GeVs. So they appear when square root of S bigger than the square root of S threshold. So another property, which I have mentioned, energy and momentum loss. Another important property is that the energies of electron and muon in different events were different. So they observed something like 24 events in the first run of the experiment, and in each of these events they measured energy of electron and muon, and they varied. So which means that we deal here with continuous spectrum of electrons and muons. Finally, what has been found that the number of events with E plus and mu minus was approximately the same as the number of events with E minus and mu plus.
That's why we didn't put the charges on the right side. Right?
This is why not I'm putting, but yeah, I can put here mu plus, E minus, and mu minus, E plus. Not there. I don't know how they put this. So, question is how you would interpret this event. So what is so you observe this event and
Neutrinos.
what?
Okay.
What neutrinos are doing. So how you would what is behind this type of event? So how they are produced? So what is interpretation? Okay, yeah, some new particle. Okay. So how you would reproduce this event? So what happens? You have E plus, E minus in initial state. Well, you see, this is typical situation. So we are now also having some unusual events. It's always. Most of them although disappear because it's somehow maybe statistical fluctuation or something like this. But yeah, so theoreticians always face such a situation. There are some events, and then the question is how to explain them. Of course, very often experimentalists themselves already give interpretations, so they have no time to interfere. But some are long-term problems, and some events which are so E plus, E minus then what you need to have? You need to have electron, muon in final state, and something which takes energy and momentum. And so the question is how to connect these things. So X, you are saying, a new particle. Okay, so how you produce this particle? You plus or minus annihilate into this particle, or what is the idea?
It should be either neutral or a pair of particle-antiparticle with a charge conservation.
Yeah, charge conservation, yeah, better too. So,
We have this threshold energy, so there should be kind of particle at rest, maybe.
with mass 3.6 GeVs. Okay, so that's mx equals 3.6 GeVs. You are saying, and it is produced like you have E plus, E minus, and then you have this particle x, right? So that's your idea. Then yeah, you will satisfy this property. Some neutral particle.
This particle, maybe I don't know if it's important observation, but it's different than the decay of muon particle, because muon particle we have pair of electron neutrino with the same flavor, and we have neutrino, which is, so we have two currents, E mu mu, but here we have different currents. We have maybe EU with mu current. So this is yeah, that in relation, but also maybe the physics different and then are
Of course, you can invent some new dynamics, but let's try first using dynamics which we know, just playing with some production of new particles, as you are saying. Well, I'm asking this question actually every year, and once we spend a lot of time, I said, still they should, to give the answer. Only once students managed to answer completely. Probably some new, actually, I suspect that somebody just you should actually tell. So you have some particle physics courses, come on.
If it's only one particle, then it should have spin 0, because you plus
Or 1, it can be 1 still, right, integer. No, but in the first place, let us try really to find what is, how you will get to this final state. Right? So what is? Well, some of you have particle physics courses. Come on. This is one of the important discoveries, and the people got the Nobel Prize for this. That's not too many. Actually, in particle physics, okay, maybe not small, but still, this is one of the major discoveries with a number of applications.
Maybe there were two different decays. Maybe there were two different decays of this particle, and one decay on a pair of electrons and neutrino, and the other was neon.
Right, so, but what happens if you produce just one particle? And this is single event. It's not like you have one event with muon and another event with electron. So that's produced in a single at once.
Are these 3 particles, or maybe?
You ask me, again. tomorrow you will open, check the publications, and you find that someone has observed some events. So then the question is, what is this?
It might be a difficulty if E plus and E minus connect still the electron, then some new particle that change to the same particle, and that particle will annihilate to give mu.
So you want to have a single particle which produces mu and E. I still missed. You want to have two new particles or what?
Yeah, two because.
So you still have, you want to have this vertex or not? This type of interaction, or what? You may have something like, of course, something like exchange here. So you may have E plus, E minus, and then some exchange, and you may get here this E minus again, something like this if this is neutral current, but then it's not clear what happens here. You want to have this. So this is this is what we call S channel. This is T channel. So what you want to have? Tell me. You want to have what? You see, I want still you to appreciate, because when I will write, you say, okay, this is trivial. Come on. I mean, you would not even appreciate completely. I would not stop and we start to discuss. But even this kind of simple steps. Of course, you right way probably logic is to start to construct something using minimal number of new entities. So let's say, okay, so let's introduce one new particle. So let's try to play with one new particle to reproduce this. Yeah.
So we don't have any baryons, so there should not be any baryon structure or any. We couldn't explain quarks.
Yeah. Well, in principle, a priori you don't know. Maybe you need at some point quark, maybe not. A priori you don't know. It may happen that you have some still hadrons, and then the hadrons decay into.
So at least it's temporary, at least, because on both sides we don't see any baryons.
That's, yeah.
So if you produce.
No, you may still have here something like pi zero, which you missed, or something, some neutral meson. When I'm saying nothing, it can be some neutral particle which just escape observations.
Is X0, we have a single vertex that goes into two leptons, lepton and anti-lepton, and there's each lepton decays then.
You want to have this one? Some
And then
new lepton or what?
Meson.
So here, what is here?
an anti-lepton. They'll
L. You want to have?
then each of them decays in one mu and the other one in E. So
How it decays?
one in mu.
Yeah, but so you have here mu, but other particles, what?
Or
Or
neutrinos.
neutrinos.
Neutrino.
Something like this, right? So you
Yeah,
are saying
three
mu,
body, yeah.
and this is neutrino, and this is
E.
E, and this is neutrino.
And then the neutrino of the new lepton.
Yeah, so the only problem with this, immediately I can tell you, so if you have this decay, then the energies of these two guys should be the same, because we are in lab system, right?
Yeah.
And therefore, if you have such a decay, which also fixes the energy of muon and neutrino, you would expect the same energy of muon and electron in all decays.
So at some point we need to have a three-body decay to have this result.
Yes, so what?
But at which point?
Huh?
At which point, I don't know, but at some point we need to have three bodies.
Right.
But then we have two neutrinos.
Maybe the first one is lepton, anti-lepton.
What? Sorry.
In each of the second two vertices we have also the other neutrino.
Okay.
So we have three-body decay there.
Okay. So that explains
The
continuous spectrum,
spectrum.
right? So what else? So, but you introduce now two new particles, right? So, and what is actually this 3.6? This is the mass of this particle or mass of what? So he wants you to have this particle with a mass 3.6 GeVs, and then you have such a decay with some new particle.
This frequency is twice the mass of the new electron.
Okay, so we are really close to. So
How did we explain lepton decays? Like, what causes electron to decay?
well, we had such an example when we have, for instance, muon, and muon decays into electron and two neutrinos, right? So then that would be kind of analogy of this decay, right? But now with new lepton, okay? So instead of mu, I'll take you as you wanted this L. Why not? Yeah. So I'm introducing the L and corresponding neutrino if you want. And so now, yeah. So again, what is important also to use already information which we had before, and then things become trivial. And you know, one thing is which is very trivial is that this is just photon. And then you have here what we call tau lepton, tau plus, for instance. Here is tau minus. And you can explain threshold effect if the masses of these two guys is just 1.8 GeVs. Okay? So then that's it. So here we have muon, and this we introduce mu neutrino, which corresponds to this charged lepton. And here we have mu E and the corresponding tau neutrino. Just tau minus, here is minus, a lepton antineutrino, and this is here, and that will be anti-tau. Here it will be mu plus and mu neutrino. So this is complete interpretation of this event. Not difficult, right? But it takes some time to recover everything. So we explain all these properties. Again, let me tell you that that is final interpretation, but then people discuss also if this is lepton, this is what is the spin of this particle, maybe the spin is 3/2, maybe this is 1/2, or what is this. So I'm giving final interpretation. We have E plus E minus, which then are producing tau plus and tau minus. And those have decays. They have decay into E plus, sorry, it's, yeah, E plus, nu E, and nu tau. Or it may have decay mu plus, mu, and nu tau. These in turn have decay mu minus, mu, nu tau, or E minus nu E and nu tau. So it can be actually 4 different combinations. It can be in final state this and this, but it may be this and that will be just E plus E minus in final state, which is nothing strange. You still have background. So it may have mu plus and E minus, but it may be mu plus and mu minus. Okay, so there are 4 different combinations. So tau can decay into different modes, as you see here. So what has been established that the mass of this particle is 1.777 GeVs, and the lifetime, which is typical lifetime for the weak interaction, 4.6 10 to the minus 13 seconds, and you will have some exercise related to this. So we started 15 minutes later. It takes some 15 minutes more. Now, spin of these particles should be semi-integer because we have here particles with spin 1/2, and the simplest possibility is that spin is 1/2. And more or less it is clear that that is kind of extension of what we learned before. We should introduce current, which contains nu tau gamma mu 1 minus gamma 5 tau. So this is G mu tau. And then have all this algebra of currents which we already discussed before, so that this current can couple with current with electron, it can couple with the current with muon, and in this way you can reproduce all these couplings which appear here. Okay? So here we deal with the product of the current of tau and muon. Here the product of current tau and the electron current with electron and electron neutrino. Okay, so what are the consequences? What are implications of this discovery? So this is discovery of a new charge lepton. So now we have problem, we have electron, we have muon, and we have tau. So remember the problem why we need to have particles with practically the same properties at fundamental level, but just different masses. And here the mass is much bigger than the mass of muon. So here we have the first kind of sign of existence of the third generation. Of fermions. So if we again apply quark-lepton similarity, we may expect that it should be some also quark family, so new quarks exist. And this is the first site of existence of third family of quarks, which has been discussed a year before by Kobayashi and Maskawa in connection to explanation of CP violation. That will be our next topic.
It's third generation of leptons or fermions?
Sorry?
Third generation of leptons or fermions?
Yeah, I have written fermions. So it's clear that it should be third generation of leptons because we have now new E, new mu, and now we should introduce new tau and tau. Of course, the question was again if new tau the same as new mu or new E, or it is different tau neutrino. Practically nobody was in doubt that this should be some new neutrino. That was actually established in the year 2000 explicitly. So it was, as in the previous discoveries, tau neutrino has been produced in one point, and then it produced a tau lepton in another point. So that was, well, nobody is going to give Nobel Prize for this. So it's interesting. Before previous discoveries, there were Nobel Prizes here. No. So we now introduce new doublet, which corresponds to new current, which is written here. So what else? The next we introduce a new lepton number. So the third, so new lepton number. We have introduced already two, but now we introduce lepton number L tau, and we ascribe to tau lepton and corresponding neutrino, lepton number 1, and lepton number for antiparticles, -1, and all other leptons, muon, electron, they have 0 tau lepton number. So now we have 3 lepton numbers. And what I was telling already, that this was the first sign of existence of the third generation of fermions, quarks and leptons. Questions? after this, of course, people start to think about mixing of all the three generations. So now I will start new topic, and we will continue on Monday. So we will discuss discovery of the third generation of quarks, and in particular big quark. Introduction of this third family of quarks actually has been related to some theoretical issues. Let me probably write first big quark. And introduction is related to attempt to explain CP violation. So CP violation, let me write explicitly. So the third generation of quarks has been introduced theoretically, proposed, then it was discovered. And in attempt to explain CP violation in nature. So what is this? Let me just give brief introduction, but we will discuss CP violation at length later. So we have V minus A structure of currents. One can check that this V minus A structure violates parity. So to say your Lagrangian, which contains this V minus A current, is not invariant under change of the one of the coordinates, or three simultaneously, which is equivalent. So fundamental Lagrangian is not invariant with respect to transformation left to right, as we are saying, or reflection. Z go to minus Z, if you want. It is not invariant. And this is because of this V minus A. You will have an exercise to check this. Not only we will discuss discovery of this parity violation. That has been discovered in 50s. Simultaneously, this V minus structure violates C parity. Symmetry with respect to charge conjugation. Again, you do charge conjugation and you get Lagrangian which changes. Again, because of this V minus A structure. For a while, people saw that, okay, P is violated, C is violated, but maybe combined transformation, C and P is conserved. And in fact, if you just write this Hamiltonian, which we have already written for weak interactions with these currents, they conserve CP, because when you do first C transformation and then P transformation, you are coming back to the same structure of the Hamiltonian. Again, we will do this exercise. But then in 1964, it was found that even CP is broken. So, 1964, even CP is broken. And in 1973, Kobayashi and Maskawa have explained how CP can be broken. Amazingly, that was one of the simplest explanations. But it turned out that after many years, till now, after many observations of CP in various systems, still everything is explained by the simplest mechanism proposed by Kobayashi and Maskawa. You have a question?
Yes, the historical directionists, they found something that violates parity or charge, and somebody puts the axial curve term in the Lagrangian because of
Yes.
So then we have a VA equivalent structure
Yes.
which conserves CP. And
Yes.
these guys do not touch the VA structure.
Which means that there's some other origin of this CP. It's not because of this V minus A structure. CP is broken by what I will just discuss. So I will try to kind of arrange my course in a slightly different way, so that first to discuss somewhere in the beginning this parity violation, but then I have found that maybe it's easy when all this kind of group of the questions about the symmetries and symmetry violation is in one section. So this is why we haven't yet discussed this parity violation of CP and CP. I will discuss this everything at once, in very general grounds. So that will be very easy to understand. So what is this Kobayashi-Maskawa mechanism? Actually, they knew already standard model already had been introduced. The proposal of Kobayashi and Maskawa, and they got Nobel Prize for this. Just don't ignore this fact. So CP violation, what they are saying, is the consequence of complex mixing parameters. So let me give you just a few, maybe one explanation, and then one more comment, and then we will continue. So we introduced already mixing parameter. Remember, one of these was this Kabiba mixing parameter. And we just have written that this is real. Well, in principle, it can be complex. So you can add some phase. You can put a cosine or sine theta Kabiba multiplied by exponent I phi. Okay? So in principle, that violates already CP. And let me just briefly mention, then we'll stop. Suppose you have Lagrangian or Hamiltonian, which can be written as lambda, coupling constant. And this is operator made of fields, plus lambda star or dagger. And this is just Hermitian conjugate, right? So we always write in this way because we want to have our energy to be positively determined. So lambda is lambda complex constant. Which is in principle complex quantity. Okay? And again, these are operators made of fields. It can be four fermionic operator, for instance, which we have discussed, maybe something else. It doesn't matter for us. So under CP transformation, what happens is this operator go to conjugate and conjugate go to operate itself. So that is CP transformation. Basically produces this type of the transformations. So if we apply this to our Lagrangian, what we will get is L go to L CP, which equals lambda or dagger plus lambda conjugate O, right? So just this becomes a dagger and this becomes O without dagger. And clearly we will have equality lambda equals lambda transformed if lambda is a small l is lambda is real, right? And then we have invariance. So I want just to say that actually things are simple. You need to introduce some complex parameters somewhere in your Lagrangian, and then you will get that this Lagrangian lead to some processes with CP violation. And this is what Kobayashi Masukawa have claimed, that they are saying that CP is because of mixing parameters are complex. Quark mixing parameters are complex. So let me write this out. The price of this statement is Nobel Prize. Can you imagine this? No, it's not a joke. It's not a joke. It's not a joke. You can do this. No, come on. Well, there's some technical issue, but essentially this is the main idea. The origin of CP violation are complex mixing parameters. We introduce one parameter complex, but one parameter is Kabiba angle. So you can make it complex, or you can have the phase. The only problem you need to deal with is that it should be physical complex phase. You may introduce various complex phases in different places, but they have no physical manifestations, just for simple reason that you eventually compute moduli square of the amplitude. You compute amplitude, but then compute moduli square. And many phases just disappear when you compute this moduli square. So which means that you need to introduce this complex phase in such a way that it doesn't disappear when you compute your probabilities for cross-section. Okay, so we'll discuss this some more.